Hello everyone, welcome to our project presentation. My name is Nilarpan Banerjee, currently pursuing my final year of Masters from Kalyani University. The project members who are also associated are Rohit Paul, Pramit Bhomik, Rudran Sarkar and Somadipta Sen. We have completed the project under the guidance of our respected professor Dr.ganesh Dutta, without whom our work is incomplete. Project title: Car Price Prediction Using R. A Chinese automobile company, Geely Auto, had collected the data. We get the data from kaggle.com. The data set contains columns, namely car ID, symboling, car name, and so on. Of them, the last one, that is the price, is our dependent variable and also known as regressor. The Excel dataset looks like something like this. The steps we have followed in our project are data cleaning, detection of outliers, model building with all variables, detecting autocorrelation, detecting multicollinearity, stepwise regression and best variable selection, model building with best variables, prediction, and finally conclusion. That is what we have learned so far. We will remove car ID, symboling, car name, car body, drive wheel, engine location, engine type and fuel system, as these variables are qualitative in nature. We have observed that two of our columns contain only two values, two qualitative values. Those are fuel type and aspiration. So we have introduced 1 for gas and 0 for diesel in case of fuel type, and 1 for STD and 0 for turbo for the case of aspiration. Our data dimension initially was 205 rows and 26 columns, but later on, as we have removed some of the variables, so the final dimension which we will work on is 205 rows and 18 columns. We have tried to find missing values using R command colsums.is.na, but we have not found any missing values, so we can freely move to our next steps. The whole data is plotted in a box plot to find outliers, and the box plot looks like this. We can see clearly that price is showing outliers, but the others are not clear. So for that case, we have to plot individual box plot. The individual box plot looks like this, and we can see that there is lot of outliers present in our data. In each of the columns, we find some outliers and replace them with the lower fence value and upper fence value of the columns accordingly. And we can see our new model, our new data has no outliers in it. Model assumptions. We have performed multiple linear regression here. The assumptions are linearity, the relationship between x, that is independent variable, and mean of y, that is dependent variable, is linear. Homoscedasticity. The variance of residuals is the same for any value of x. Independence. Observations are independent of each other. Normality. For any fixed value of x, y is normally distributed. Our data model summary looks like this. We have taken price as our dependent variable and the rest of the variables as independent variables. Residuals show if the predicted response variables are close or not to the response values that the model predicts. Standard error measures how the coefficient estimates can vary from the actual average value of the response variable. Test of significance of the model shows that there is strong evidence of a linear relationship between the variables. This is usually represented by significance stars at the end of row. For each estimated regression coefficient, the variable's p-value provides an estimate of the probability that the true coefficient is 0 given the value of the estimate. More number of stars near the p-value, more significant the variable is. And if p-values are less than significance level, null hypothesis can be safely rejected. T-statistic is the estimated value of parameter divided by its standard error. R square is the square of the correlation between two variables. Adjusted R square is preferred as it adjusts for the number of variables considered. At the end we can see F statistic. Basically F statistics define collective effect of all predictor values on the response variable. Now we will plot the model. The first one is residual versus fitted, second one is normal QQ plot, third one is scale location, and finally the fourth one is residuals versus leverage. The first one tells us about our linearity assumption. The second one holds for normality condition. The third one is for checking homoscedasticity, and the fourth one tells whether our data contains any influential point or not using Cook's distance. Now we will proceed to detect autocorrelation. Autocorrelation is a characteristic of data which shows the degree of similarity between the values of same variable. The hypothesis for Darwin-Watson test are H0, that is our null hypothesis, says there is no first order autocorrelation, whereas our alternate suggests that there is presence of correlation. The Darwin-Watson test statistics look something like this given in the diagram. The Darwin-Watson test reports a statistic with a value from 0 to 4, where 2 represents no autocorrelation, 0 to less than 2 is positive autocorrelation, and greater than 2 to 4 is negative autocorrelation. A rule of thumb is that test statistics values in the range of 1.5 to 2.5 are relatively normal. Values outside this range could be a cause for concern. Our model gives Darwin-Watson test statistics as 1.7132 and p-value of 0.32979. According to rule of thumb and as well as from p-value, we can conclude that there is no presence of autocorrelation. So we can proceed to the next step. Now we will detect multicollinearity. Multicollinearity occurs when independent variables in a regression model are correlated. This correlation is a problem because independent variables should be independent. We will detect multicollinearity using variance inflation factor or VIF, which is given as VIF is equals to 1 by 1 minus Ri square, where Ri represents R squared values. Interpreting VIF or variance inflation factor. 1 indicates not correlated. Between 1 and 5 represent that it is moderately correlated, and greater than 5 is a problem, that is highly correlated. So we will try to remove those variables having VIF greater than 5. Before finding VIF of the model, let us look our correlation plot, where blue color indicates positive correlation and red color indicates negative correlation. Higher the set, higher the correlation present. Thus we see that multicollinearity exists and we remove them using VIF. The VIF of our model is given, and as you can see there are a lot of variables which contain VIF more than 5. This is a problem, a serious problem. It is likely to remove the highly correlated independent variables. We have removed the variables one by one and checked the correlation, and finally we have obtained a model like this where multicollinearity is not present. Now we will proceed to stepwise regression. This is forward step regression and it is suggesting a model, as you can see. Doing backward selection, we can also see there is a suggestion for a model, and doing both step selection gives the best result between backward and forward. And we can see that both step selection is giving the model of backward selection. So we will proceed with that model. This is our final model which we will work. Model summary. Now we got the best selected variables and model summary looks like this. We can see adjusted R square is around 83%. Now prediction and accuracy. We can see that the adjusted R square decreases from the initial model. Initially it was around 85%, but later on in our final model we can see that it is around 83%. We can see that adjusted R square decreases from the initial model. Correlation accuracy shows a high value of 88.7%, so it means that actual values and predicted values have similar directional movement. Before doing this correlation accuracy, we have to split the data. We have split the data in 60-40 ratio in test and train data. Now we have done min-max accuracy. Min-max accuracy is giving almost 94% accuracy, which is very good. MAP or mean absolute percentage deviation is defined as 9% almost, I can say. So it is very low and it means a very good prediction accuracy. After completing the whole project from initially outlier treatment to prediction, we understand several important things that we have to keep in mind. Those are R squared. R squared is higher the better, adjusted R squared is higher the better, statistics higher the better, and so on. We can see that clearly. We have also came across some important points. High value of R squared does not imply if a regression model provides an adequate fit to data. A good model could show a low R squared value, while on the other hand, a biased model could have high R squared value. Note, a high R squared value tends to increase as more variables are included in the model. So adjusted R squared is the preferred measure as it adjusts for the number of variables considered. And F-test compares the model with zero predictor variables and suggests whether the added coefficients improve the model. If a significant result is obtained, then the coefficients included in the model improve the model's fit. So F-statistic defines the collective effect of all predictor variables on the response variable. In our final model, we can see that our F-statistic increases, which is good. In our final model, we have find that high R squared is not obtained. Initially it was 85%, but later on it decreases to 83%. But doing accuracy, we can see that it is not much problem, as the prediction is good. We can see from min-max accuracy and as well as from MAP. I hope you have enjoyed the presentation. Thank you for your patience. Have a great day ahead.